மாணவர்கள் அனைவருக்கும் வணக்கம். Countable sets theorem. The set Q of all rational numbers is countable. Proof. Let the set A1 consisting of the element 0 by 1 minus 1 by 1 1 by 1 minus 2 by 1 2 by 1 and so on. A2 consisting of element 0 by 2 minus 1 by 2 1 by 2 minus 2 by 2 2 by 2 and so on. Likewise, we construct A3, A4 and so on. An is consisting of element 0 by n, minus 1 by n, 1 by n, minus 2 by n, 2 by n and so on. Precisely the set consisting of all the rational numbers. Each set is countable because of each set consisting of a set of all integers. Set of all integers is already countable set. So each ai is or an is countable. The countable union of countable set is countable. So we decide each n belongs to n is countable as the set of all integers is countable. Since union of an is countable, union of countable sets and therefore it is countable. But this union is precisely the set of all rational numbers, hence the set of all rational numbers is countable. So each an is countable since set of all integers is countable. So we decide countable union of countable set is countable. So the set of all rational number Q is countable. Next theorem. Next theorem. The set closed the interval 0, 1 is uncountable. Proof. This is uncountable. Suppose we take the closed interval 0, 1 is countable. This means that, which implies there exists an one-to-one onto mapping from n to the n2 closed interval 0, 1. Expressing each fn as a decimal, f of 1 equal to 0.a11, a21, a31 and so on. F of 2 equal to 0.1, a12, a22, a32 and so on. F of 3 is equal to 0.a13, a23, a33 and so on. Likewise, we construct f of n equal to 0.a1n, a2n, a3n and so on. Here all aij belongs to this set consisting of element 1, 2, 3 and so on 9. So each value of aij belongs to 1, 2, 3 and so on. This is a diagram for the closed interval 0, 1 consisting of the decimal values between 0 and 1 which is uncountable. We will going to prove the closed interval 0, 1 is uncountable. Let us choose for each n belongs to n a positive integer bn as follows. Bn equal to 1 if an not equal to 1. Bn equal to 2 if an equal to 1. Suppose if a11 equal to 1, we choose b1 equal to 2 here. A11 equal to 1, we choose b1 equal to 2. If a11 not equal to 1, we choose b1 equal to 1. Likewise for b2, b3 and so on. This means that for each n, bn not equal to ann. We construct the decimal value y equal to 0. B1, b2 and so on. Suppose b1 equal to 1, a11 not equal to 1. This purpose for each f of n is differ from at least one place of y. Differ from at least one place of y. So y belongs to the closed interval 0, 1 and y does not belongs to f of 1, f of 2, f of 3. Since y is differ from at least one place of f of n. Next, since y is differ from f of 1 in the first decimal place because b1 not equal to a11, it is differ from f of 2 in the second decimal place. It is differ from f of n in the nth decimal place. Also, the decimal expansion of y is unique since no bn is equal to 0 or 9. This means that y not equal to f of n for any n. We have thus found a real number which is in 0, closed interval 0, 1, but which is not in the set consisting of the element f of 1, f of 2 and so on f of n. This is contradicts the assumption that closed interval 0, 1 is countable. Hence 0, 1 is uncountable. இந்த அளவிலே இந்த வகுப்பை நிறைவு செய்து கொண்டு அடுத்த வகுப்பிலே சந்திப்போம். வணக்கம்.